Welcome to the ECE Colloquium. It's a pleasure to have today with us Professor Behnaam Aazhang from Rice University. Dr. Aazhang received his degrees, BS, MS, and PhD from University of Illinois, Urbana-Champaign, and then joined in 1985, joined Rice University, where he's currently the Abercrombie Professor in the ECE. He's also the director of the Rice Neuroengineering Initiative, as well as the co-director of Houston Methodist and Rice University Center for Translational Neuroprosthetics and Interfaces. He served also as the chair of electrical engineering, electrical and computer engineering at Rice University for many years, and he also has held an Academy of Finland distinguished visiting professorship at the University of Oulu in Finland. Dr. Aazhang is a fellow of IEEE, AAAS, and a distinguished lecturer of IEEE Communication Society. He received an honorary degree also from University of Oulu, Finland, which is basically the highest degree, the highest honor a university can bestow to its guests. And for those of you, those younger people here, of course, Dr. Aazhang, if you don't know who he is, he's the who's who of wireless communication. For those of you who are kind of up and coming to the field. With that, welcome, thank you for coming, and the floor is yours.
Okay, good morning, everybody. It is hard to live up to the introduction that Hamid said. That is very generous, thank you. Today, I'm going to talk about what we have been working on over the last 10 years or so. As Hamid said, I used to do a lot of work in the wireless area. It was a lot of fun and enjoyed it very much. And then a few years ago, maybe by now 10, 12 years ago, one of my colleagues and I decided to see what else can we do to have fun, all right? And I decided to go in the space of neuroscience, and he decided to go to the space of what he called later digital health, which is an interesting topic. And we went our own separate ways, and today I'm going to talk about my path, all right? And I'm going to present it as a story, and as opposed to just a whole bunch of equations and a lot of details, because they asked me to talk to a very broad audience and not very sort of focused audience in this particular topic, okay? Therefore, it's going to be a very broad presentation, and also that I would love it if you ask questions, all right? I would feel very good about myself and my talk and the fact that I spent time preparing this thing if you have questions, if you ask questions during the talk, after the talk, next week or next month, all right? Now, that's how I feel that I was successful. And is that okay if I point here? Is that, for those of you guys on this side, is that okay if I point here? Or you want me to point there? Okay, 50-50. 50-50, all right, I go 50-50, all right. Now, I'm going to explain what this neuroengineering initiative is, and sort of, as I said, and as Hamid said, I started out my career in wireless, and I did a lot of signal processing and information theory, which I love both subjects. And the question is, how can you bring that subject and those set of tools to this new application area? That's all this is all about, all right? Now, when you think about medicine, and you can imagine what's going on, this is basically, from my perspective, this is what's going on in the field of medicine, all right? Basically, you go to a doctor and you have an issue. You don't go to a doctor if you don't have an issue. And the doctor tries to understand the issue, tries to examine the issue, and based on the issue, what the issue is, develops an idea, a therapy. And mostly, it's all about pharmaceutical solution, which makes a lot of sense, pharmaceutical solution. But many of the solutions are not patient-specific. Basically, one pharmaceutical solution they give you, for instance, they give to basically hundreds of thousands of people across the US, across the world, right? And the question is that what do engineers know and do, right? What we do is that we develop tools, we sense, just like the doctors, we try to find out what's wrong, what's going on, we sense, we learn, and then we try to come up with therapeutical solution, therapeutical protocols, all right? But one subtle difference is that many of our solutions are patient-specific. We get data from you and then turn that data into a solution that is specific to you. And that is, in my opinion, that's a one subtle difference between clinical work and what engineers can do, all right? Now, a couple of very prominent examples that have been around for the last 10 years or so is deep brain stimulation. We all know and can have a feel of what that means. It basically means that they insert an electrode into the skull, through the brain tissue, and they stimulate the brain for various reasons, all right? And believe it or not, it works for many disorders, all right? Do we know why it works? Not quite, right? You may have heard that it works often, but we really don't know why it works, all right? But as long as it works, that's great. And I hope you have seen some videos of a patient that has Parkinson's, and they do these deep brain stimulation, and the patient stops the tremor, right? And it's just fascinating videos that you can watch on YouTube, right? Other examples are in cardiology, for instance, right? You all have heard of pacemakers. If your heart has issues pumping, they put a pacemaker on the heart tissue, and then it paces the heart instead of the heart pacing, all right? Paces the heart properly for the heart to function, all right? And I just recently learned about this concept of left ventricle assist device, which is, to me, is fascinating, that if you have serious heart disease, a heart failure, that means that, as an example, that means that your left ventricle is not functioning, all right? And that is where the blood goes into the body. What they do is they intervene, and they take the blood out of the left ventricle, put it through a pump, and then pump it back out to your body. To me, that's fascinating, and for many patients that have almost heart failure, this is a lifesaver and improves the life of their patient by 5, 20, 30 years, right? Examples of what engineers can do to help in the clinical setting, right? And there are tons of other examples. These examples, to me, are fascinating, and I just put it up there, all right? Now, what we have done at Rice, Rice is a private university, and we were all doing our own things, and then we decided to sort of focus on this area of what we call neuroengineering. And we put together a whole bunch of faculty, all hired over the last 10 years or so, and they covered a very large spectrum of topics and expertise. They're across 4 different engineering departments at Rice, and we collaborate with at least 3 medical centers across the street from Rice. For those of you who have been to Rice, you know that Rice is literally across the street from world's largest medical center. And in that medical center, there are multiple medical schools, and we work with many, many of them, all right? And the spectrum is very broad. It starts with me, that I'm a signal processing type. You can call me a machine learning type, okay? I don't mind. And I work with data, all right? I work with signals and data, all the way to Jersey, who works on the molecular level, cell level issues, and he develops biomarkers. He manipulates individual cells or population of cells to, again, deal with disorders and many issues of that sort. And anything in between, from cell level to all the way to signal level at the high level, right? And then, as an example, Chong is a material scientist, and he develops what we call flexible electrodes. Electrodes that are flexible, that penetrate into the brain cells, brain tissue, and there are thousands of them, 1,000 channels of recordings, and out of those 1,000 channels, maybe 100 of them can actually stimulate as well. Therefore, they record and they stimulate, all right? And these are very flexible, very thin, and just incredible technology that he brings to the table in this particular space, all right? And this is what we put together with the last 10 years or so, and you could imagine that very successful group, a lot of funding, a lot of graduate students and all that. And we are not a department, right? We are an institute, but our previous provost did not like the word institute. And I'm like, okay, you give me $75 million, you can call it Jack. I don't care. As long as we can build this thing, I really don't care what you call it. She could like to call it initiative, all right? I still ask this question, why initiative, why not center, why not institute? I really don't care, all right?
You got the money.
I got the money, thank you, thank you, thank you. All right, now let's focus on what I do, all right? As I said before, I am a signal processing information theorist, just like Hamid and Dror, and this is what I work on, all right? I work on specific disorders and trying to understand the circuits, the population of neurons that are responsible for that particular disorders, all right? And the list of disorders, this is what I have today. But if you, I'm not married to this list, but this is a very fascinating list to me. And I work on these kind of things. And we have various fundings to work on these kind of projects and all that, all right? And today, I am only going to talk about one of them. I'm not going to give you a list of things that we have done. I'm just going to talk about one thing. My story is going to be a story of one thing that we work on this project, all right? I'm an engineer, right? I don't just try to understand. I try to help, right? And not only trying to understand, but I also work on modulation technologies to mitigate the disorders, all right? And trying to understand when you modulate, why does it work? Why does modulation really stops tremor, as an example, all right? Excuse me. Okay, that's what I do. And in my team, we have all of these people that I want to acknowledge them before I get started. And these are my graduate students. These are my colleagues. I am not a builder. Tayun Chi is my colleague who is a hardware person, and he's been working with me on these kind of projects to actually build hardware that would help mitigate the different disorders, all right? And I talk about Paul's work. He's a soft material type person, and we are working on something called sleeping cap, and I'll talk about that in a bit later, all right? And today I'm going to talk about Anton's work and Fatime's work. All these three are actual Rice undergraduates that stayed at Rice and joined my research group. And Fatime is originally from Pakistan, and she's, I'm going to talk about some of her work as well, right? And again, as an engineer, you cannot work by yourself. If you're working just by yourself, you're wasting your time and resources, all right? You got to work with clinicians. You got to work with clinicians for multiple reasons. One is that they understand the disorder, they understand the disease, they understand the physiology of the brain, all right? They understand it much, much, much better than somebody like me could. And that they have data. They have data, they have patients. Now, these colleagues of mine are in Houston Methodist, in incredibly large hospitals that they have, let's say, stroke patients. My colleague here, who is a neurosurgeon, does stroke patient work and surgery on stroke patients, maybe 10 of them a week, all right? You can imagine how much data he could give me to work on, all right? and other people in that group. We have a radiologist, and we have people that actually work with patients and collect data and all that. All right? Therefore, it's very, very critical to work with clinicians that actually have access to patients and data and all that. All right? And the project that I'm going to talk about today has a very substantial correlation with sleep. All right? Therefore, I'll talk about it in a second. And therefore, it's very important for us to work with a sleep expert. It turns out that these guys are all in Methodist Hospital, and she is a sleep expert in Baylor College of Medicine, both of them being across the street from Rice. All right? Now, today's talk is going to I'm not going to give you a long list of this project and that project and all that. I'm going to tell you one story. And the story is a complete story from A to Z. And the first part is a part that we just finished, very happy ending kind of story. And the second part, we are in the middle of it, all right? Therefore, there's no ending yet. But we are, as academicians, we're always hopeful, right? You got to be hopeful. Otherwise, why are you doing this thing if you are pessimistic, right? Therefore, we are very optimistic that the second half of the project is going to work also. And therefore, maybe in a year or two, we will have a complete story that is a happy ending story, all right? Now, the one that I'm going to talk about today, the story is about Alzheimer's, all right? And we all know what Alzheimer's is, and many of us know people who have been affected by Alzheimer's, all right? And it's a sad story, and let's see what can be learned about Alzheimer's, all right? It turns out that Alzheimer's is a neurodegenerative disorder, and it is a form of dementia. And dementia is the big picture name for the disorder. Alzheimer's is a part of it, is a subset of it. And it is believed that Alzheimer's starts out with a poor flow of cerebrospinal fluid flow. All right? This is supposedly a brain. It's a depiction that I stole from Wikipedia or from Google. And this is supposedly a brain, and this side of it depicts a patient with severe Alzheimer's, and this part supposedly depicts a patient that's healthy, all right? And basically, what happens is that the brain, or at least this side of the brain, shrinks, and its functionality reduces quite a bit. And the reason what they believe to be the case is that the CSF flow becomes poor, becomes low, all right? What does CSF do? CSF is all about, this is the artery, the red one's artery, and CSF is a flow next to the arteries, and basically it is responsible for the cleaning of metabolites and other proteins that misfold, all right? And it cleans them out, right? And throughout your life, you have junk build up in your brain, and the functionality of CSF is to clean it out. Right? Basically, you could see a young person like you guys having a whole bunch of metabolic waste, and the CSF flow goes from here to there and then cleans these up and then sends it to this lymphatic system. Yes, sir?
Okay, but we're all wondering, how do we take steps when we're young to avoid this stuff or reduce this stuff? Like, we don't want all these electronics in our brain. We want to kind of like drink coffee. Oh, drink coffee. Okay, I'll go get extra.
Yeah. Don't know. The short answer and the good answer, don't know, and that's exactly what we're doing. We are trying to find out non-invasive ways to help patients that have early onset of Alzheimer's, all right? The short and long answer is the same. We don't know, all right? The question is that why a person who is healthy and has a beautiful flow of CSF, cerebrospinal fluid, how come it goes from here to there where the fluid flow is not natural and complete, all right? Don't know, all right? And then the last picture that you see here is the one that the patient has Alzheimer's, and you see here the flow is missing, a whole bunch of waste has been created, but not much has been cleared out, all right? Now, to go back to Dror's question, how do we know we have an issue with CSF, right? And then if we do have a flow, what can we do to improve the flow, right? That's the whole premise of our work, all right? It's not like you can take aspirin and that helps. I don't think there is such thing. Therefore, you may be able to exercise more or do a lot of brain exercises, but it's not clear at this point, all right? But what we know that most of this glymphatic flow or CSF flow happens during sleep, all right? One idea would be to get enough sleep, all right? To get enough sleep because most of the cleaning happens during sleep, all right? That's one thing. And it does decrease when you have traumatic brain injury, and it does decrease even when you have a mild traumatic brain injury, all right? A traumatic brain injury, you know what that is, and mild traumatic brain injury is basically concussion or multiple concussions that you may have, all right? It is all related. Therefore, if you have a mild traumatic brain injury, that's going to reduce your CSF flow. If you don't get enough sleep, that also can reduce your glymphatic flow, CSF flow, all right? And that's one reason why Department of Defense is interested in these kind of projects, because they have soldiers that don't get enough sleep, and they have soldiers that are susceptible to mild traumatic brain injury, and they want to understand what's going on, all right? Did I answer your question? Get enough sleep.
Wait. You're telling PhD students that?
Okay, forget what I just said.
Round of applause, please.
Do you want them to have CSF flow issues?
Well, this is an audience at risk.
That's right. That's right. I can help, by the way. All right. But this is what's going on, right? This is the whole picture. That's how much you understand about CSF flow and how much you understand about clearing brain waste, right? Now remember, our whole body has a system of waste clearance called the lymphatic, right? The word glymphatic or CSF flow is very similar. There is a letter G in there for glial. That is basically the lymphatic system when it comes to the brain, all right? But we have waste clearance throughout our body, all right? Now, how do you measure CSF, or how do you measure flow of CSF? You know there is a lot of flow going on, which is your blood through your brain. And how could you focus on CSF instead of just measuring the blood flow, right? And it turns out that that's not an easy problem. Measuring the flow of your brain is not an easy problem. And it turns out that you can measure the CSF flow if you do an MRI, all right? Not CT scan, MRI, all right? And in not just any MRI, a 7 Tesla MRI. It's called a phase contrast 7 Tesla MRI. And it basically, the phase contrast, and 7 Tesla gives you, the phase 7 Tesla gives you enough resolution. The phase contrast, basically what it does is that it gives you the contrast that you could use the phase to estimate the velocity, all right? Phase on one location, phase in another location, the difference between them shows you the velocity, all right? And you could do that and then estimate the velocity or estimate the flow of your CSF. You can focus your image on the parts that you recognize to be CSF, not blood, and then you have an estimate. We have done that, and this is a 7 Tesla MRI image, and this little dot in here is called aqueduct, all right? That is in the center of the brain, and that's many of the CSF flows goes through that one point. And we were able to estimate the velocity, estimate the area, multiply the two together, get the flow, all right? A few things about this plot, which is kind of to me and to us is interesting. First is that the flow is, the velocity is positive and it goes to negative. Therefore, flow is this way and that way, a lot this way, a little that way. Therefore, the balance is what gives you the whole flow, all right? And second thing that is interesting is that these are a number of patients that we did the MRI on, and the flow was very different, quite different among all of them, even though the trend was the same, but the value of the flow was quite different between them, all right? Another thing that we observed that hasn't been reported in literature is that the size of the aqueduct changes from patient to patient. It's not all the same. It's not because anatomically it could be that one person's aqueduct is bigger than others and all that. And the multiplication of these two gives you the flow, all right? And when you look at these green and the blue ones, you recognize or think that, okay, maybe they don't have enough CSF flow, right? It turns out that hang on to those two patients or those two subjects, and we talk about them later again, all right? It turns out that these are all healthy subjects, all right? Volunteers that we paid them like $25 to put themselves to a 7 Tesla MRI to get these things. I'm not $25, but maybe a little more, all right? I don't know the number, all right? Have you ever been to a 7 Tesla MRI room? Good, because it is really challenging. It's really freaky, basically. Maybe 3 Tesla you have been to, but 7 Tesla is a different game. It is very intense, and my own graduate student goes there and works with the patients, and every time he goes, he gets a bit nauseated, and it's a very freaky experience. I've never been even close to one. Not too many places have 7 Tesla MRI. Houston Methodist has. Houston Methodist has more 7 Tesla MRI than many countries do. All right, that's just sad. But anyway, this is how it looks. All right. And then the question that we were asked again by folks from DOD is that, is it possible to measure the CSF flow indirectly and not to an MRI machine? All right? Obviously, the answer is yes. Otherwise, I wouldn't stand here and talk about it, right? The answer is yes. But at the time, we didn't know whether the answer would be yes. This was a true research question. All right? And this is what we envisioned, right? That remember that CSF happens mostly during your sleep. Therefore, you can sleep with a cap like this, hopefully. All right? And also keep in mind that it is impossible to sleep inside the 7 Tesla MRI machine. Impossible, all right? Therefore, we would take measurements from a subject during MRI, and then later this afternoon, we would test the same patient later in the afternoon with some of these modalities and compare to see if we can reconstruct the flow that we just saw a second ago. All right? Surprisingly, the answer is yes, even though it's not synchronous. All right? If you wish it was synchronous, that you do MRI at the same time to do these tests, but there is no way that you could test this equipment inside the 7 Tesla MRI. All right? It's impossible. At the same time, it's impossible to sleep in a machine like that. But with these devices, the subjects actually sleep through the whole night, and you observe them and then measure the CSF flow. Yes?
Does CSF flow behave similarly if you're sedated versus when you're asleep?
I don't know.
Okay.
Don't know. We could do it.
Might be worth an experiment.
Say again?
Might be worth an experiment.
Might be worth experiment, but getting volunteers to say yes to that is harder. Yeah. We could do it when they have other surgeries, right? If they're going there for some other surgeries, maybe open heart surgery, something like that, we can put the stuff on their head and do that. But that's a very different protocol and a very different challenge than what we were able to do. Yeah. Make sense? Very good question. Yes?
Kind of follow up to that, like, can this be done on like other animal models, mice?
The short and long answer is yes. And mice is just maybe too small. We are thinking bigger animals, right? But then if you could do it safely on humans, right, why would you go to a smaller animal, right? I think the reason is that this could be done easily, and we have found some 25 or so volunteers to do this thing for $100 or something. And why would you go to the smaller animals, right? Because we care about humans, right? Right? Especially that is if these ideas are non-invasive and easy to manage. But good question. Anything else? All right. How much time do I have? 15 minutes? No.
Half an hour.
Jose?
Yeah, but 20 minutes, 25 minutes.
25 minutes, okay. Thank you for your generosity. All right. Okay, let me pick up the pace a bit, all right? But still, I would like to get questions, all right? And these are the modalities that we are trying, okay? We have tried, all right? Some of them you recognize, EEG, EKG, we all know what those are. PPG is basically something similar to oximeter, all right? Basically measures your blood oxygen level and is optical based and all that. And it turns out that before this project started, I asked my colleagues who are clinicians that say, if you are a betting person, among all of these modalities, which one do you think is going to give you the best answers? And all of them said the last one, transcranial Doppler, which is basically like a speeding gun that policemen use. They basically put the gun near you to measure your speed, right? Doppler comes in, signal comes in and comes back, and they find the speed. Basically, you do that transcranial, meaning you put the gun here and then look for the flow and measure the flow, which is basically something that moves. And then they all said transcranial Doppler. And they were all wrong, all right? And it was not very useful. It was very hard to do it right, all right? And then we eliminated others and only focused on these three modalities, all right? And then basically what we did is that we took some patients, put them through MRI, 24 patients, and then on the same patients, later in the day, we did these tests, all right? 2 of the patients after the MRI, they said, okay, I have enough, good night, I'm going home, all right? 2 of them we lost, but then the other 22 stayed with the project. And then based on those 22 patients, we built a model, and then we tested the model on 15 patients that we have never seen before as a cohort, validation cohort, all right? And we built something like this, a flow diagram like that, basically a machine learning diagram, all right, that pre-processes, extracts features and all that. And then these are basically typical EEG signals. We looked at them in the time domain. We looked at them in the frequency domain. We also looked at the correlation between the spatial relationship between the signals. And also that we build graphical features based on the data, all right? Basically, these are transitions in the sleep stages. Again, sleep a lot to do with this, all right? Therefore, altogether, we had 4 physiological signals, as you see the list here, and we had 2 sleep day signals, all right? Altogether, and then that makes a 6. And we fuse everything together. We have 7 signals to deal with to extract features and use the feature, give the features to a regressor to give you this waveform that we want, all right? And then we measure the difference between the waveform that this data gives you to the waveform that the MRI gives you, and look at the root mean square, look at the Pearson correlation, all that, see how close we are to rebuilding this thing from the data that is not MRI data. Make sense? All right. And an example of machine learning, again, this talk is about how we did this thing, and we did not innovate at all when it comes to going from features to regression and all that. We only innovated in the feature part, extracting the right features, all right? And as I said before, the one that we bet on was the worst one. Therefore, other signals was much more powerful than the one that we bet on, all right?
So how did you establish the fact that the 4 features that you have bet on were irrelevant in some sense?
I think if you do it right, and you point the transcranial Doppler in the right direction, catch the right flow, it would be fine. But it's very hard to do because these paravascular openings are very small. Therefore, it's very hard to point the right direction. And that's why it failed. It wasn't that the technique failed, it's just that pointing this gun is the wrong word to use in this context. Pointing this in the right direction was nearly impossible. Right? But then Doppler, based measurement of velocity works beautifully, right? Could work beautifully. But then the fact that these spaces are so narrow, and they are not straight narrow. There are some straight parts, but then some curvatures and all that is really hard to do that. That's what happened. That's why their guess was that is a good guess, but turned out to be the wrong guess. Right? Anything else? And this is the whole block diagram of what we did. And this is what we were looking for. Remember that? Remember that we were looking for signals like that to give you the flow. And this is the result, right? Using some off-the-shelf regression ideas. Off-the-shelf meaning that I teach it in my class, there are textbooks on them and all that. And it turned out that lasso and ridge regression worked very nicely. And this is the one that gives you Pearson correlation, the R of the Pearson correlation, and it's pretty good numbers, right? This is from the cohort that we used to build the model, and this is from the cohort that we never seen before, therefore what we call the validation cohort, all right? Of course, a little less than the cohort that we've seen before, but it's still pretty good correlation. And this is the root mean square of that, basically, again, the difference of the signals across the time period, all right? Now, one thing that I forgot to say is that this period from here to there is one heartbeat, R to R, right? One heartbeat, therefore there's basically 1 second. And we had many of these one heartbeats that we observed, therefore we didn't have that many patients. And that's why we were kind of very careful with our analysis and with our regression and feature selection, because it's not that one of these features are going to be having a lot of information. It's just that the information is really distributed among all of these modalities. All right? As you see here, not one of these modalities dominated. All together, they had enough information to help you estimate what you're looking for, but individually, none of them dominated. All right? Even TCD that we talked about before didn't dominate. All right? All right, and then, yes?
So even during sleep, you're going to have some stages where your heart rate's going to be higher and your heart rate's going to be smaller.
Yes.
Lower. So you're going to measure the CSF flow per heartbeat. So in a range where it's going to be lower versus higher, do you notice any differences?
Not really, because even though we did use heart rate variation as one of the features, but in terms of final result, not because of the fact that so many features. Okay. Therefore, one got buried, even though heart rate variation was one of the features, but it got buried into so many features that we had. Very good question, though. All right. And then what we did was that we said, okay, we have an idea that seems to work, all right? Let's make it practical, right? Therefore, we build a set of electrodes that would do EEG and do EKG and do PPG for you, and put it all into this headgear, and then took all the data and put it into this OpenBCI platform that exists out there off the shelf, and it brings all the data in and has enough ports to integrate all the data. And then wirelessly, using Bluetooth, connects to Raspberry Pi, which is the off-the-shelf microprocessor, and then processes the data and implements all of their block diagram that I showed you earlier, and it spits out the number. It spits out the regression flow number across a heartbeat. And we feel like we're done. We're done with this part of the project, all right? Now, is it possible to sleep this on? No, it is ridiculously difficult to sleep on. But we are working with one of our colleagues that I mentioned earlier on developing something like that, but with a soft cap, all right? Using materials that are soft and would have electrodes in them so that you could actually sleep in this thing, all right? But that is sort of the next phase, all right? But it works. The question is that, what is the next thing to do? Next big thing to do, okay? Let's say that we have a patient that has a low CSF flow, as Dror mentioned. How can you help that patient, all right? How can you help that patient? It turns out that in general, neuromodulation has been very successful in restoring brain functionality, restoring brain circuit, because our brain is an electrical system, and modulation, careful modulation in the right location could really help, right? And it has been proven or shown to help. And also in some studies on animal models, it has been shown to improve CSF flow. Exactly don't know why. CSF is not necessarily a charged fluid, but it seems to work, all right? The question then is, this DBS is very invasive, as you see here, and is very hard to manage, and is hard to put in the right place, and very complicated and requires a neurosurgeon. The question is there anything else that we could do in this space to help, all right? And we have an idea, all right? And the idea is this, all right? This is a radio tower that generates radio frequency. We all know what this is, and we all use it every day. And this can create a beam, supposedly a narrow beam, and that beam can bring in radio frequency energy to a particular location, all right? Then what if we put a whole bunch of these on the brain tissue or outside the skull, which would be very non-invasive, all right, if there is such a word, and generate signal and a beam going down the brain tissue, and this beam would run at, let's say, gigahertz, all right, gigahertz frequency, RF frequency. The question is, what is it going to do to all the neurons along the way, all right? This is the signal that I just talked about. It looks like a flat, but no, it's actually a lot of variations inside. With this time scale, it is impossible to see the variations. And this is the response of a single neuron when you impose this signal on that neuron, all right? Now, how do we do that? Using biophysical models. Our biophysical models have been around for a long time. And basically, they solve Hodgkin-Huxley equations to look at the response of neurons to any environment, including imposing this. And we see that this signal does not solicit anything from the neurons, basically. That suggests that our cell phones that we are using and putting near our ear is safe, because of the fact that the frequency that it has is safe, and it doesn't elicit response from any of the neurons along the way, all right? And what if you do the same with 100 hertz frequency, all right? A signal like this, the green signal, at 100 hertz frequency, that is a typical frequency that we use for deep brain stimulation. And what it does is that it elicits response from neurons and makes neurons fire, all right? This is a very dramatic picture. All it does is that it increases the probability of firing. Not that it fires all the time, it's just that this is, I like drama, and this is very dramatic depiction of that, all right? Therefore, if we were focused on 100 hertz, we could elicit some response, all right? What if we do this, all right? Have two beams, the green beam at 3 gigahertz or 2.4 gigahertz, and the blue thing at the same frequency except for 100 hertz difference between the two. All right? When they superimpose and hit the red spot, the red focal point, what you're going to get is the summation of two cosines. We all know what that means. That means that we're going to get DC term plus 100 hertz signal. All right? And this concept, in general, is called temporal interference. Has been published 10 years ago or so. And this is the implementation of that, or variations of that with radio frequencies and gigahertz range frequencies. All right? What it does is that it elicits response from neurons, just like before, but only in the red parts, not through the whole beam. All right? And again, the neuronal response was simulated using Hodgkin-Huxley model and biophysical model, and it seemed to work. All right? What else needs to be done, right? We have done this work, we simulated it, and we used it to understand what does it, because it brings energy to the brain. What does it do to the temperature of the brain tissue? All right? That was very important. If the tissue is heated up beyond 1 Celsius, that is off the table, because that is never going to be approved by FDA. It has to be less than 1 Celsius to be approved, hopefully by FDA. Our simulations suggest that it is less than 1 Celsius. We have done biophysical modeling of that. You saw that already. We have done heat simulations of that. You saw it already. And we are now working on phantom experiments, meaning that put the antennas around the Petri dish and put electrodes in the middle and see whether you can actually build a multiple antenna and get signals the way you want it in the middle when the two beams interact. All right? And of course, none of this matters if it doesn't work in animal models. We go back to the animal model that he asked. This time, we want to do animal models because the proof is going to only happen when you have animal models. All right? Our animal of choice is pigs. The reason is that pigs have big enough brain, but much easier to work with than primates, non-human primates. And this is going to be our next step, to have this experiment. Yes?
So, sorry, I had a quick question about the signals interacting. Is there any concern with them reflecting in the brain and then constructing or being constructive in a different part of the brain?
Absolutely. There is a concern. Yeah, absolutely. Our hope is that we only give enough energy so that the reflections would lose so much energy that would be irrelevant, all right? Therefore, what you see here in this physical and biophysical model, we gave enough energy to get a response, right? If you lower the energy level of the signal, you won't get much, all right? Therefore, our game plan is that to do it at a level, careful level, so that the red signals would have enough energy, but other reflections and all that would, by then the signal had really died, so that they would not have the same. But you're right, though, the skull reflects the different brain tissue, white matter, gray matter, and their boundaries are going to reflect. Yes, absolutely. But we're not going to know till we do experiments, right? Sir?
Yeah, I can't help but think, I guess, and I wonder if you guys have sort of looked at the problem that way. You know, you were able, with a certain number of factors, whatever, you know, the measurements and the sensors you've used to actually model that CSF flow. Mm-hmm. Then the question that sort of comes up is, have you looked maybe at the causality aspect of any of those sensors that would give you maybe a flatter, in other words, a low CSF thing? so that you can use that as a basis of, pinpointing the, I don't know if that's the case, but
No,
it
no.
seems to me that,
No, we haven't. But it's a good question, though. It's a good question, but we haven't. Now, remember, this is very new, right? right? Basically, the paper on the first part was just submitted to Nature Communication last week. Therefore, we just did this, and we are, I'm talking about it to get questions like this. And the short and long answer is no. But it's an open problem. Yeah. No. Unless you do animal models, the story is not finished, right? The story is not finished. But that's our next story. Basically, next step is that we are working with surgeons that do a lot of animal work, and we are working with them to experiment this thing in animal models and see what's going on. See what's going on. And if you can get that done, then you can publish and present these ideas outside. All right? Now, I thought you were going to ask this question. All right? Basically, if you have a way to measure CSF flow in real time, which we have, all right, the question is that can you use that thing and learn from the data and then adjust the parameters of stimulation to turn it back and modulate with those new parameters and have a closed loop system, right?
it's the same question.
Yeah, same question, yeah. As engineers, we all love closed loop control, right? We all love closed loop control. We all learned it in school. You guys are learning it today, these days. Control is beautiful. Closed loop control is beautiful, but we only learn it in the context of a linear system, all right? If you have a linear system with a state space that linearly relates to observations and input and observation, you're golden. You just solve a couple of equations and you're golden, right? Is our brain a linear system? No, it's not, right? The state space is large, it's not linear, but and there's no theory out there that would support a optimum closed loop system. But with data and there are some activities in nonlinear data-driven closed loop systems that we are excited about, right? And that is our next big project, right? To see if we can do this thing, not optimally. I'm not going to ever claim that what we're going to do or what we end up doing is going to be optimal, but it may, be a nice way of doing it, all right? These are the people that have supported this project and a couple of other projects related to this thing. As you see, Army is interested, again, because they're interested in sleep, soldiers with no sleep or very little sleep for days and days and days. And they're interested in patients with MTBI. Again, the relationship to MTBI I talked about already. And McNair Foundation, just a nice foundation. They're nice to us. All right? And NIH, of course, that is their cup of tea. All right? And surprisingly, NSF is also interested in the whole area of neuroengineering. All right? With that, let's hear some more questions. Yes, sir.
So before conducting this study, you must have had some assumptions about the CSF flow and the effect of it for disease like Alzheimer's.
Before the study, you're asking me if I had
any assumptions or anything expected out of this study, and once you were done with it and you obtained this signal of CSF flow, would you want to share if it changed or proved any assumption wrong?
Okay, I had no idea. Let's be clear about this thing. All right, I had no idea 3 years ago that we had something called CSF, right? I'm being honest. I had no idea, right? This question was posed to us as a bunch of engineers, and we're like, oh yeah, we can solve anything. That's how our approach was, right? And that said, I work with clinicians that do this thing for a living, right? And that's what they said about TCD, right? That's what they talk about TCD. a few things still was even surprising to them. One was this variation of velocity in the aqueduct. One was the fact that aqueduct space is so varied across patients. These are all healthy patients, right? These all two were surprises to them as well, right? And then one thing that happened was that these patients were all supposedly healthy and young, all right? They were supposedly have no issues with CSF. Okay, that's why we chose them, right? Two of them, as I mentioned before, the green and the blue one, right? It turned out that their numbers and their flow was unusual, too flat and all that. It turned out that we were kind of worried, and that really messed up our numbers. We did not exclude them from the numbers I showed you, but it did mess up our numbers. But to be honest, we couldn't exclude them because they were supposedly healthy. We went back, and well, not me, but the clinicians went back and looked at the MRI of these two subjects, and they identified serious issues with them in terms of their MRI of the brain, and they were not surprised that the CSF behaved poorly. And then they alerted them that, hey, you think you're healthy, and you, in your answers in the survey, you said, I'm very healthy, blah, blah, blah. You have issues. And those were subjects that work in Methodist, and they volunteered for these kind of things, and they were alerted that you have some issues. I'm not sure if I answered your question. Yes, sir.
I have a question. In terms of treatment, if you may call it that way, if you catch these let's call them limitations, kind of pointing to a potential Alzheimer's, does
Modulation.
This modulation still kind of alleviate and mitigate some of these issues?
The modulation in terms of DBS has been shown in a number of papers that improves the CSF flow on animal models.
But not on humans.
No, because DBS, if you have a CSF flow that is low, that's not enough to do a DBS. Enough issue to do DBS. They do DBS for OCD, they do DBS for PTSD, they do EPS for severe depression and all that, but not for a low CSF. That's not approved by FDA, as an example. They do for Parkinson's and many other disorders, but not, yeah. But that's why they do it for animal models.
Isn't it a prelude to Alzheimer's, though?
Yeah, but Alzheimer's may come down 10 years down the road, 5 years down the road.
Yeah, but if you can avoid it, why not? In other words, if this modulation works, and you can help it, why not?
I think the barrier to putting a DBS electrode in your brain tissue is maybe too much. That's why I think if our idea works, it's going to be non-invasive. Therefore, then we maybe have a chance, but not DBS, to my knowledge. Yes, sir.
I understand that this is a pretty long workflow, and there are a couple of stages here, and even errors in every stage, they can accumulate over time, and you have a really low number of patients, considering like 40, as you mentioned. So I'm a bit concerned about I'd say the generalability of this concept. And I understand that you have maybe low patients that have old tests, but there are quite people that take the MRI, quite people that take EEG. It might not be everything, every test, but there are a lot of people that take each of them, so one of them maybe. We might be able to generate the other signals for these people, so that might be helpful. And I'm also concerned about your loss. You're considering the CSF as negative of your loss function. Is that correct? If the flow decreases, then you consider that it causes.
Oh yeah, okay, yeah.
But that might not be the case. Body has many other options, and we're not sure if that is the sole case that's causing Alzheimer's.
Is a hypothesis, yes, absolutely, yeah.
It might not be a cause, it might be an effect of it.
Sure.
The very base of your studies might be incorrect as well. Like you're basing your studies on that this is the cause, and if we're able to mitigate this, then it will cause this. It might not be the case.
Very pessimistic, though. Which is fine. Nothing wrong with having a pessimistic question. As a faculty member, you cannot be pessimistic, right? But the question is that, is it okay to be naively optimistic, right? Now, that said, let me try to answer your question. Our limitation is not with finding patients that are going to subject themselves to a non-invasive, a sleeping cap and all that. That's not our, we can get 100 patients like that, and that number would be great, right? But it's going to be very hard to find patients that subject themselves to or subjects, forget about patients, to 7 Tesla phase contrast MRI. That's the problem. Right? That's why our N is small, right? If our N was 2 million, this problem would not be trivial, but would be much easier to solve, right? That's one point. The other point is that all we can do is that rely on other studies that suggest that poor CSF flow is a precursor to Alzheimer's or early onset of Alzheimer's, all right? Because that's not what we do. You give us a problem, we solve, right? They gave us a problem saying that CSF flow, poor CSF flow is a precursor to Alzheimer's, and we worked on this, right? Now, intuitively, does it work? Does it make sense, right? I would say yes, because our body is very used to clearing its waste, right? If the waste clearing system is poorly functioning, there got to be something wrong with our brain then. If it's not Alzheimer's, it could be something else, but cannot be a good thing to build up a lot of waste in our brain, right? And now that's what we are working on. That's what we focused on, right? Make sense? And yeah, that's all I got. All right. I'm sorry about calling you a pessimist, but your question was a bit pessimistic. Not you. You must be very optimistic. All right. Anything else? Please, yes.
So when you do the 7 Tesla MRI, you get a lot of information about what is happening in different parts of the brain.
Yes.
Maybe there's high CSF flow in one place. Are you looking at non-invasive ways to get that information as well, or have you just decided that it's okay to just have the
Well, what do you mean by non-invasive ways of getting that information? Because the way we understand it is that the gold standard of estimating CSF flow is 7 Tesla MRI, right? That's what we understand, and there is no other alternatives to estimate CSF flow in any location of the brain, all right? And that's the hypothesis that we went with. Is that the question?
Yeah, I kind of meant like you have a device that works pretty well, right, to estimate just the overall CSF flow. But were there other sensors or something else that you looked at to say, hey, maybe we can predict CSF flow in specific locations?
The only, well, not that we know of, okay? Let me just answer that this way first. But the only location that we focused on was the aqueduct, which is the center of the brain that all the flows go in. Our hypothesis was that if you can estimate the CSF flow through that aqueduct that is in the middle of the brain, and it basically the flow goes down and reaches to the lymphatic flow and then flows out of the body, right? Now, our hypothesis is that if the flow is low in that spot, that is highly correlated with the concept that flow is low everywhere. All right? Did that answer your question?
Yeah.
All right. All right. And yeah, that's all we have, right? We had to focus somewhere, and then to us, focusing on the center where all the flows goes through was the most natural way, all right? 2 more questions. Yes, sir.
Well, you have the model for estimating the cerebral fluid based on these measurement, EEG, ECG, PPG, and all that. So you use the machine learning to use those features extracted from those physiological data to replicate or estimate the curve for your So is there any biological model that links these other physiological signals to the flow? For example, the circulatory system, because most of the signal that you are getting there is coming from the circulatory system.
Yeah.
Or anything that links those two from the biological point of view.
Not really, right? That's why I believe that we were not able to focus on one measurement or one modality. I am thinking or guessing that the information that we are chasing is buried into a number of signals, buried. Therefore, all we could do is that extract that information. And that information was not dominated by one signal. As you saw in the table, different scenarios, different modalities worked a little better than others. All together, they worked well. And then I genuinely believe that the information is distributed, and there is not one modality that directly measures the flow. And the TCD that I was talking about, the transcranial Doppler, would have been, that was everybody's guess, because that really measures the flow directly, not directly, but indirectly, but actually measures flow. But then because of, as I mentioned to Hamid, because of the fact that those openings are so small, it's really hard to do a TCD focused on that. And then you may end up getting a blood flow as opposed to CSF flow. That's why we abandoned that. It really was a waste of time, in a way. And unfortunately, there is no neurophysiological parameter that directly measures the flow.
I'm going to ask a last question.
Yes, sir.
Okay, was there anything that was established in terms of this CSF flow, and then the ultimate onset of Alzheimer's, which is also, I guess, has been shown to demonstrate or highly correlated with these patches in the brain tissue?
Not that we know, but our next phase is, because remember, all of this were healthy patients, right?
Yes.
Our next game plan is to actually do all of these measurements, possibly even MRI on subjects that have either hydrocephalus, which I did not talk about it much at all, because CSF flow is basically the sole responsible for hydrocephalus, right? And the flow breaks or some other thing happen, and then you have hydrocephalus. That's a very big challenge, all right? And therefore, our next step is to either go to patient or both, go to patient with hydrocephalus and patients with Alzheimer's and examine our estimations, our flow estimations, and give a little bit of more clinical value to the work. Right now, we just work with healthy subjects, except for the 2 that happen to be non-healthy. But the question is, how does any of these things work in an actual patient with some serious issues?
Okay, let's thank our speaker again.